Hello everyone. Today I'll present my work on AI-enhanced sensor fusion. Here is the outline of my presentation. I'll now begin with the introduction. To start, let's look at what motivated the study and the problem that it aims to address. When we think of the word manual, we think of things that we would rather not do ourselves, things that are better automated. This is exactly where digital twins and autonomous vehicles come into the picture. Imagine a robot moving around and doing a task for you. But for such a robot to work, it needs to mirror the physical systems accurately. The virtual model needs to know exactly where the real system is. That requires precise position estimates, and these are achieved through sensor fusion. Multiple sensors provide partial information, and Kalman filters have been the classical way to combine them into a single reliable output. In this Venn diagram, the left part shows the classical sensor fusion methods, including the Kalman filter. On the right, we have the purely AI-based methods. In between, we have the hybrid methods, which aim to combine the structure and stability of classical filters with the learning ability of AI. The key question for us is, can this give us the best of both worlds? And that's exactly what this work aims to investigate. Now let's look at the methodology. This slide gives an overview of the testbed setup, which includes both software and hardware components. On the hardware side, the experiments were conducted in a demo room equipped with multiple sensor systems mounted on structural frames with tracking units attached to an automated guided vehicle. On the software sides, we had two key components. A mock sensor node simulated real-time data streams from offline sensor readings. The sensor fusion node ran the classical, hybrid, and AI-based pipelines. In our classical sensor fusion approach, we used the extended Kalman filter. This is because it's a well-established standard in robotics and localization. It's lightweight and real-time capable and handles moderate nonlinearity. So it's a really good benchmark for comparison against the hybrid and AI-based methods. This slide shows the mathematical formulation behind the extended Kalman filter. I won't go into the details here, but it's included to illustrate the foundations of this approach. Before talking about the hybrid and the AI-based fusion approaches, I wanted to introduce the GRU, which is an integral part of these two approaches. In this work, I have used a gated recurrent unit, or a GRU, which is a type of recurrent neural network designed to handle sequential data, just like sensor readings. Think of it like watching a movie. You remember the important parts, but you forget the unnecessary trivial details of the movie. This is exactly what's happening in a GRU. The update gate decides how much of the past information should be kept, like the EKF error patterns. The reset gate decides how much of the old error history to ignore, for example, to handle outliers or sudden spikes. The hybrid fusion approach keeps the basic Kalman filter structure but adds a learned correction stage on top of it. The EKF first produces its usual fused position estimate from the sensor inputs. Then a GRU model looks at the past EKF outputs and predicts the residual error in that estimate. Finally, this predicted error is subtracted from the EKF output, giving us a compensated and a more accurate position estimate. The AI-based approach has removed the EKF completely. Here we rely only on the neural network. The GRU model takes in a short sequence of raw sensor readings and directly predicts the AGV's X and Y position. Now let's move on to the experimental setup. Before we talk about the experiments, I'd like to point out what evaluation metrics we used in this project. We considered three in total: mean average error, root mean squared error, and the mean Euclidean error. The mean Euclidean error was the main metric for comparing in all of our experiments. To begin the experiments, we first started with the model selection. to determine which GRU architecture performed best for both fusion approaches, the AI-based one as well as the hybrid one. We used Optuna for the hyperparameter search. So this library automatically tests different parameter combinations and suggests the best configuration for the GRU. It changes the hidden layers and dropout rates and then suggests a configuration for us. Now let's look at the results. These plots show the results for the 10 GRU variants tested in both hybrid and AI-based setups. The AI-based models have a much larger error spread since they do not do since they do direct fusion without the EKF structure and stability. The best models achieved lower errors, but they did need more memory and training time, but still their inference time stayed within the real-time limit. The next part focuses on the real-time evaluation. This experiment has three parts, each covering a different evaluation aspect. The first sub-experiment here focuses on trajectory comparison, how closely each method follows the ground truth. In this plot, the black line represents the ground truth trajectory. We can see that the hybrid EKF stays closest overall, although it slightly overcompensates in some areas. The classical and AI-based models follow similar paths, but with larger deviations from the ground truth. We can see these differences more clearly in the average error values on the next slide. We can see that the error in the hybrid EKF is lower than the other two. To better understand the spatial context of the errors across the trajectory, we also generated these heat maps. We also wanted to know how different the errors are in the XY directions, and hence there are two separate graphs for these. Finally, we move to the last sub-experiment. This figure compares the cumulative distribution function of the Euclidean errors across all three fusion approaches. A left shift in the curve indicates that more time steps fall within the lower error values. You can see that the hybrid EKF is consistently left shifted compared to the classical EKF, meaning that it achieves lower errors for most of the trajectory. However, in some higher error regions, the curve flattens, and this suggests that there has been occasional overcompensation. The AI-based model shows a smoother profile and in some segments even dips below the classical EKF. Now let's conclude the paper. This plot summarizes the overall comparison of all systems. The x-axis shows the mean Euclidean error, and the y-axis shows the update or fusion interval. The best performing systems are the ones that are closest to the bottom left corner, meaning that it has low error and low latency. We can see that the raw sensor systems perform the worst, which is expected. They have both higher error and slow update intervals. The classical EKF and the pure AI models improve over the raw sensor readings, but still maintain away from the ideal region. The hybrid models, on the other hand, they are clustered closest to the ideal operating point. So our key takeaway is hybrid fusion strikes the best balance between accuracy and responsiveness, and it outperforms both model-based and purely data-driven approaches. As with any research work, there is always room for further exploration, and I've listed a few possible extensions here. Thank you for listening.